Hi, my name is Manish Gupta, and in this video, I'm going to talk about PLAID, which is basically a dense retrieval system for late interaction retrieval. It's an efficient engine for late interaction retrieval. Okay. So PLAID is a revised version of ColBERT v2. I recently recorded the ColBERT v2 video where the idea is that it's a dense retrieval system where on one side you have questions and the other side you have passages, and you want to retrieve relevant passages for those questions. The questions are represented in terms of its tokens. Passages are also represented in terms of its tokens. And there's an embedding for every question token and an embedding for every passage token. And you figure out the most relevant passages by ranking them using this maximum similarity score. And the maximum similarity score basically says that for every query token, you're going to find the most matching document token in the embedding space, and you return those documents or passages which have the highest sum of such maximum similarities across all the query tokens. Okay, so that's that. So basically the way ColBERT works, for every query token, you basically try to first get centroids. So in ColBERT v2, essentially they have this notion of centroids where rather than storing document tokens and looking up document tokens, they actually store centroids in the nearest neighbor index. So essentially for every query vector, you try to figure out distances, closest nearest neighbor, 1 to 4, 1, 2, or 4 centroids, right? And then for each of those centroids, you actually also maintain an inverted index or an inverted list, which basically maps those centroids to the passage embedding token IDs, right? So you basically retrieve those token IDs, quite a lot of them, 2 2 raised to 12, 2 raised to 14 such token IDs. And once you have figured those out, you essentially try to get their embeddings. The embeddings for the passage tokens are not stored as is. In fact, what you end up storing is the nearest centroid's ID, and also a quantized 1-bit or 2-bit quantized embedding for each of those document or the passage tokens, right? So therefore, at online inference time, you essentially figure out the nearest centroids. For those centroids, you basically figure out passage tokens which are closest to those centroids, decompress them, compute their cosine similarity with each query vector. And then you compute the maxim and a lower bound to the maxim per query token by grouping those scores by passage IDs for each query vector, right? So this is basically a recap of what I actually discussed in the previous video anyway, right? Now you sum up these lower bounds across the query IDs so as to essentially get the maxim similarity scores, and you get the top scoring candidates. Now for those top scoring candidates, you essentially load the complete set of passage token embeddings and then compute the exact maxim similarity scores. You sort the passages by those scores and return to the user, return as the output from the system, right? So one of the problems with ColBERT v2 is that it is slow. So although ColBERT v2 was shown to be faster than ColBERT, but well, it's slow, right? So it's more accurate than ColBERT, but it's slow. And the problem, what PLAID folks did is to essentially also look into what slows down ColBERT v2, right? So overall, in the online inference part of ColBERT v2, there are these 5 steps. So query encoding, when you get a query, you encode the query, you generate the candidates by looking up those centroids and then those passage tokens, which basically are close to those centroids. And therefore you take those documents as candidates, right? And then you do an index lookup so as to figure out other tokens of those documents. You decompress, essentially you try to get the non-quantized versions of those document token embeddings, and then you score, right? So all of those basically take various amounts of time. So here is a split of the time, right? So essentially you observe that index lookup and decompression takes a whole bunch of time. So while what PLAID does, PLAID essentially tries to just really, reduce that time, index lookup and the decompression time significantly. So of course it increases the candidate generation time. However, as you can see, index lookup and decompression time is completely sort of gone from, from PLAID. PLAID rightly stands for performance optimized late interaction driver. Okay, so that's that. Now, how does PLAID do this, right? So essentially, but there are a few things which PLAID implements on top of ColBERT v2, and I'll discuss more on the next slide. But mostly what it does is rather than actually, in the inverted index, rather than storing embedding IDs, it basically stores passage IDs themselves, right? That's one thing that it does. The other thing that it does is that rather than actually doing a matching between the query token and the embedding token and the passage token, query token and the passage token by by decompressing the passage token, they essentially just do the similarity between the query token and the centroid of the passage token, the closest centroid to the passage token. Okay. So as a filtering step. Now, is that a good filtering step is the question, right? And to answer that question, you see in this picture, what they've done is that for two data sets, they've shown some curves, right? And they basically say that, hey, if you take top 10 passages from ColBERT V2, right? What is the recall of these top 10? So if you basically found out top 10 candidate passages using ColBERT V2, right? So on the other hand, in PLAID, you're actually not generating candidates by doing decompression of the passage tokens. You're actually just matching with the centroids themselves, right? Centroid embeddings. So if you do that, right, what is the probability that you will get your the ColBERT V2's top 10 in PLAID's top 100, for example, right? So sure, I mean, because you're doing some approximations, you're not really computing the exact similarity with the document passage tokens. So therefore, there will be approximations. So you're actually ignoring the residual in some ways. But if I basically increase that k from 10 to, let's say, 100, am I able to capture those 10 by a significant probability, right? And it turns out that yes, at 100, you can actually capture 99% of those of those passages that ColBERT V2 would have provided to you. Okay, so therefore the candidate generation phase, as you can see, basically is a little longer. So it generates much more candidates, 10x the number of candidates that ColBERT V2 would have generated. However, the remaining phases, the index lookup and the decompression make up for it. And overall, therefore, the amount of time that ColBERT that PLAID takes basically is much lower than ColBERT V2. Okay. So that's one optimization. The other optimization is that thinking is that given a query queue, right? If you basically look at the matching document tokens, those document tokens do not really belong to too many clusters. They basically belong to a very few number of clusters. Okay. So given a query queue, only a small subset of the passage embedding clusters tend to be far more important than others in determining relevance. Okay. So essentially, if you basically look at a query and you try to compute its similarity with various passage tokens, you would observe that the maximum values essentially the most of the contribution to the maximum values comes from very few clusters, right? This is the CDF part, maximum centroid score. And as you can actually see, it's basically coming from a very, very small subset of the passage embedding clusters, which basically means that you can actually, before you actually compute the maximum values, you can actually filter out a whole bunch of passage tokens, which do not belong to similar embedding clusters, similar clusters. Okay. So that's that. So now that drives the methodology of PLAID. Okay, so the way PLAID works is in basically these four stages. There's an initial candidate generation. There is a centroid interaction with pruning as a filtering step. And then there is a centroid interaction without pruning. And then you have a final ranking with decompression. This last step of final ranking with decompression is really exactly the same thing as ColBERT V2. However, the first three steps essentially do a whole bunch of candidate generation and filtering, which makes PLAID much, much faster. Okay. So let's go over this pipeline, right? So what happens in the first stage, initial candidate generation? What happens at that point, right? So there are these query embeddings and there are these centroids. So where do these centroids come from? Of course, you have basically, taken your passage tokens, you have computed their embeddings, you have basically, done, you did k-means clustering like you did do in ColBERT V2, and you stored them into your index, right? So that's where you get these cluster centroids. So these centroids are essentially passage token centroids, right? At candidate generation phase, you use the inverted index. This inverted index is basically a map of centroid to passage IDs. Remember in ColBERT V2, it is a map of centroid to embedding IDs or passage token IDs, right? But in PLAID, basically it's a map from centroid to passage IDs that ensures that this index is actually much smaller. It's about 3x smaller in size because the number of tokens, you can sort of imagine number of tokens are much more compared to the number of documents themselves, right? So basically this index is essentially 3x smaller in size. So you use this inverted index. Essentially, you take the query tokens Q, right? So Q represents the matrix of query tokens, embeddings of the query token query token embeddings, and C is basically the matrix of centroids. So you compute the distance between centroids. Every centroid and every query token. And remember, this could be hundreds of thousands of centroids. So this is a matrix multiplication, and that's not really too large a matrix multiplication, hundreds of thousands of centroids, and probably expressed in, let's say 768 or 128 dimensional space, as is there in ColBERT v2. And query embeddings, well, maybe like 5 or 10 query embeddings, again, expressed in 128 dimensional space, right? So you compute the similarity, and the similarity basically tells you the nearest top k centroids, right? So nearest top k centroids. Now you take those centroids and you essentially, those centroids, you have mapped them to passage IDs. So any passage ID that belongs to these top k centroids is basically a candidate passage ID. Okay. So you give that to the next phase, which is centroid interaction with pruning. So what happens in this phase? So essentially the idea is that, you basically obtained some passages and you also have these centroids. So you take those centroids and you essentially in this pruning stage, in that senses, you actually score only those passage tokens whose matching centroid score is greater than TCS. I mean, well, there is a threshold that you keep that, hey, I'm basically, a threshold on what? Threshold on similarity with the query tokens. So if some centroids are really not very similar to the query tokens, you sort of throw away those centroids from your, from your list in that senses. Okay. So now what are you left with? So you have like some passage IDs which have been selected here. And those passage IDs, of course, contain your tokens, so passage tokens. So what you could do is, you have to compute similarity. I mean, you have to rank these passage IDs, right? Which are good ones and therefore filter out not so good ones. Okay. So you essentially take each of those tokens in these passages, right? And then you compute the maximum scores with respect to the query tokens. Now, in general, computing these maximum scores in ColBERT v2, you would decompress these passage tokens and then do a proper maximum computation. However, to make it super fast, you don't decompress. Remember, decompression used to take a lot of time. So therefore, you don't decompress these passage tokens. Okay, so you essentially just compute the similarity between the query and the closest centroid for these passage tokens. Okay, so that's called centroid interaction. Approximate the per passage relevance by substituting each token's embedding vector with its nearest centroid maxim. You ignore the residual part, so you don't really bother about the decompression at all at this stage, right? And also one other thing is, for every passage token, there's a nearest centroid. And if that centroid basically has a score less than similarity score with the query tokens less than TCS, you ignore those centroids anyway. Okay. So the interesting part is that you basically get rid of a whole bunch of documents because their query tokens, their passage tokens actually belonged to centroids which have a very small score with respect to similarity score with the query tokens, right? So you remove those centroids in this stage. And then in the next stage, you basically, yes, you compute, similarity between the remaining passages and the query tokens in terms of the centroid interactions. After you've done that, now you're left with really, really relevant top K, passage IDs. Now you take those passage IDs and you actually, compute the exact maximum similarity. And the way you would do that exact maximum similarity computation is by actually decompressing. So take the residuals, decompress them, get the actual passage token embeddings, and you then actually compute the true relevance scores, which is the true maximum similarity basically. And you, of course, return the top K. Okay. So this part, the last stage, as I mentioned, is basically the same as ColBERT v2. However, the first three stages actually lead to a significant, the first stage, in fact, leads to much more number of candidates than ColBERT v2. But these two stages actually reduce the number of candidates significantly. They filter them out too much. Filter them out a lot. Okay. Now, one little thinking about the centroid interaction. So these maximality score computations basically are super fast. They're super fast because they can actually make use of the same similarity scores that you computed here. Remember, you are basically now trying to compute for any query token the closest centroid for a particular passage token. Similarity between them. And remember that similarity is already computed in this matrix. So when you want to really compute in stage 3, when you're computing this approximate maxim, well, that does not really require any new dot products. Those dot products have already been computed. You just reuse those scores. Because that's why it becomes very fast. Okay. Now, a little bit note about across these various stages, when you're essentially doing computations, actually, they've designed fast optimized kernels for data movement, decompression, final scoring, all of them, which basically makes these stages even more faster. So they've done basically, a little bit of CPU and GPU optimizations, kernel optimizations, just to make it even faster. So how does PLAID perform, right? So, well, they basically measure performance across 4 different datasets: MS Marco V1, Wikipedia, which are both in-domain datasets, and they also measure performance on the ColBERT V2 introduced Lotte pool dataset, and MS Marco V2, which are out-of-domain datasets. Okay. These datasets vary in terms of their number of passages, number of tokens, number of queries, and so on, right? And if you look at the index size, the vanilla ColBERT V2 index size, those sizes are much larger compared to the PLAID index sizes, right? And this reduction in index size, as I mentioned, is basically because the inverted inverted list, no longer maps from centroid to passage token IDs. Basically, it maps from centroid to passage IDs, which reduces the index size quite some. Okay. So that's that. So now how does it perform across MS Marco, V1, and so on, all of these data sets? So, we have results across all the 4 data sets here. This is for MS Marco V1. On the right side, you basically see the results for Wikipedia. Then you see the results for Latte pool. And then lastly, you essentially see the results for MS Marco V2. Okay. So there's comparison being done with multiple other systems, BM25, Splayed V2, DPR, and BM25 again, and so on, right? However, more important is a comparison with ColBERT V2. Okay. So if you basically look at PLAID, right, and K, so K is set to 10, 100, or 1,000. What is this K? Well, the K is essentially, how many passages do you retrieve? So finally the candidate generation, this guy, right? It basically finally gets how many passages for the final stage to run, right? So this K, basically, if you vary from K equal to 10 to 1,000, what do you observe? You observe that the MRR value, 39.8, is very similar to 39.7 that you can obtain from ColBERT V2. Okay. So similarly, other metrics are very, very similar, right? As you see, they're very, very similar to ColBERT V2. However, if you look at latency, well, look at the latency. I mean, one CPU latency basically becomes 10x smaller, right? 8 CPU, again, almost 9 to 10x gains in latency, right? Reduction in latency. GPU latency does not reduce too much, but still, if you observe, right, 259 milliseconds becomes 38 milliseconds. That's massive reduction in latency. Okay. And the trends are very, very similar across data sets. So if you basically look at, again, I mean, in general, if you really think about it, if you compare with ColBERT V1, right, the latency for ColBERT V1 is actually higher compared to the latency for ColBERT V2. Okay. Similarly, if you compare it with other methods, you would observe that typically the latencies for ColBERT V2 are significantly lower, while the accuracy metrics basically are better than most of the baseline systems and comparable with ColBERT V2 itself. Okay. So that's about PLAID. I mean, essentially, you get comparable accuracy with ColBERT V2, but much better latencies. So in summary, PLAID is essentially a late interaction retrieval system, basically meaning multi-vector dense retrieval system. Okay. It essentially involves these concepts of centroid interaction and centroid pruning. Also in the inverted lists, it basically does not, it basically stores mapping from centroids to passage IDs rather than centroids to passage token IDs, right? They've also done optimizations in terms of kernel. They use optimized fast kernels. Okay. Overall, across multiple datasets, they essentially show that you can actually obtain reduced late interaction search latencies by up to 7x on GPUs and up to 45x on CPUs against vanilla ColBERT V2, right? While you retain the same retrieval quality matrix. That's it for this video. Hope you like the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.